So it's important to be able to determine points at which the tangent line to a curve has a certain slope. That is, points at which the derivative, or the rate of change, has a certain value. So for this example, we're given a function, and we want to find the points at which the tangent line is horizontal, and also the tangent line has slope 9. Okay, first of all, for part A, we want the tangent line to be horizontal. What's the slope of a horizontal line? 0. So that means we want the slope of the tangent line to equal 0, which means we need to find the values of x for which the derivative at x equals 0, because of course the derivative is the slope of the tangent line. So then what we need to do is find the derivative of the function and then set it equal to 0 and solve for x. First of all, what's the derivative of the function? Well, we need to take the derivative of this. Now we know that we can distribute this derivative operator over the addition. And now we can just use the power rule on each of these guys to take the derivative. So for the first one, we have a constant of -1 out front, and then we have an exponent of 3. So then we do 3 times -1, and then x to the 3 minus 1 power. So we'll get x to the second power. So we'll get -3 times x squared. Okay, now we have plus the derivative of this guy. Well, this one has a constant of 6, so that's going to be out front. And then we have x to the second power, so the 2 gets moved down as a coefficient. Multiply it by the 6, so 2 times 6 is 12. And then we have x to the 2 minus 1 power, so we have x to the first power. Okay, so this is our f prime. This is our derivative function. So remember what we need. We need f prime of x to equal 0. So this is our f prime of x, and we need to set it equal to 0 and then solve for x. That will tell us the points at which the tangent line is horizontal, or the tangent line has a slope of 0. So then we set up that equation. Now we just have a quadratic equation here. So we can easily solve our quadratic equations. First of all, it's already set equal to 0, so that's good. So now let's just try to factor this left-hand side over here, which should factor very easily because it's just a binomial. So we can factor out a 3x. So we get this. Now we can set each factor equal to 0. So we get x equals 0, or we get x equals 4. So whenever x equals 0, or whenever x equals 4, the derivative will equal 0, or the tangent line will have a 0 slope, or the tangent line will be horizontal. Now they asked us to find points on the graph, so we need to find coordinate pairs. So now it's going to find the corresponding y value for these coordinate pairs. So we know x equals 0 corresponds to the ordered pair 0, f of 0. So to figure out what that ordered pair is, we need to figure out what f of 0 is. So f of 0 is just whatever value we get when we plug 0 into our original function, which just gives us 0. So we have the ordered pair 0, 0. Now let's find the ordered pair that we get when x equals 4. So that corresponds to the ordered pair 4, and then f evaluated at 4. So let's figure out what f evaluated at 4 equals. So f evaluated at 4 will equal 32. So that means this ordered pair is equal to 4, 32. So we found 2 points on the graph where the tangent line is horizontal, the point 0, 0 and the point 4, 32. Now for part B, we need the tangent line to have slope of 9. That means we need the value of the derivative function to equal 9. So we already found the derivative function in the part A, so let's plug in now what the derivative function equals. So I've plugged that in here, and we need it to equal 9. Now this is a quadratic equation. This time it's not equal to 0, so first thing we need to do is subtract 9 from both sides to get this quadratic equation equal to 0. And now we'll try to factor the left-hand side. First thing we can do is factor out a -3, and now let's try to factor this trinomial. which will easily factor. Now we can divide both sides by -3 to get rid of this -3 that's sitting on the outside. And that will just leave us with x minus 3 times x minus 1 equals 0. And now we set each factor equal to 0. Then we can solve each expression to get x equals 3 and x equals 1. Now again, we want to find ordered pairs. So this corresponds to the ordered pair 3 and then f of 3. So to find f of 3, we need to plug 3 back into our original function up here. When you do that, you get 27. So we have the ordered pair 3, 27. Now x equals 1 gives us the ordered pair 1 f of 1. So now we need to figure out what f of 1 is. So we plug 1 into the function and we get 5. So that gives us the ordered pair 1, 5. So what we've done is we found the 2 points at which the tangent line, or the derivative, equals 9, or the tangent line has slope 9. So that happens at the point 3, 27 and the point 1, 5. So if you want to look at what's happening graphically, in part A we found out where the slope equals 0, or the tangent line equals 0. That's always going to happen at these local max or min. So see, it happens right here at the point 0, 0, and it happens again at the point 4, 32. And you see at those points, those are turning points in the graph, or points where we have a local min or a local max. So whenever the graph turns around like that, you're going to have a tangent line equal to 0 with slope 0, or the derivative equals 0. So that's actually one way that we can identify the locations of local max or local min by finding out when the derivative is equal to 0. And in part A, we found 2 points where the slope of the tangent line was 9. So you can see that happens here at the point 1, 5, and that happens here at the point 3, 27. So at those 2 points, the graph, or the function's rate of change, instantaneous rate of change, is the same. At both of these 2 points, we have a tangent line with slope 9, or a derivative that equals 9.